The car of the future is, of course, built upon great technology that's being innovated today. Today's state-of-the-art technology includes what is called ADAS, driver assistance, advanced driver assistance systems, that helps to keep cars and keep drivers out of harm's way. There's all kinds of technology that's available today, from cruise control that adjusts the speed depending on the car that you're following, to lane departure warnings that veers you slightly back into the center of the lane if they see you drifting too far away from the edge of to the edge of the lane when you don't have your signal lights on, to blind spot detectors, to parking assistance. ADAS technology has really evolved a great deal over the last several years. It could even help you park, do parallel parking assist. These pieces of technology are made possible largely through three basic fundamental technologies. One of them is radar. Radar has the benefit of going very far. It can detect an object, can do it well at night. It can also, of course, penetrate fog. Does their job equally well whether it's in the middle of the day or at night. Uses ultrasound technology that is relatively low cost. When you come close to something in a slow way, it can measure the distance relatively well. So when you're doing your parking and it says that you're 16 inches away, 15 inches away, 12 inches away, that technology is based on ultrasound. And of course, increasingly, we're starting to see video technology using cameras. This is the state-of-the-art of ADAS technology today. Incredible amounts of technology that is built piece by piece into the car. Each one of these detectors are autonomous or independent. Increasingly, we're also seeing that this technology is being replaced more and more by camera technology, and the reason for that is because cameras are getting better and better. Camera technology is benefiting from all of the same things that the consumerization of mobile chips is benefiting from. More mobile devices, higher resolution cameras, higher dynamic range cameras, the ability to detect image at night in dark rooms. These cameras are getting better and better over time. Increasingly, we can imagine what used to be radar systems be replaced by camera systems. Now, these cameras could be smart cameras or not smart cameras. And smart cameras are cameras that are also includes object detection. Basic computer vision technology that detects objects and warns you against car in front or pedestrian, road signs, etc. Now, one of the things that we're really excited about, as more and more of these sensors are replaced by cameras, not only are we reducing the cost dramatically, we're reducing the power that's consumed by these radar systems. We can bring these ADAS technology deeper into mainstream cars. Much of these ADAS technologies are available only in the highest end cars. But the thing that's really cool is, if we were able to replace the vast majority of these sensors with cameras, and we have the ability to unify the information that is sensed by these cameras, we might be able to do something really magical with it. If we wanted to lead towards, ultimately, driver assistance towards the road to autonomous self-driving cars, autopiloted cars, there are several things that we have to solve. The first thing that we have to solve, of course, is that the car needs to be able to build an environment model around it. If all of those cameras were connected to a central processor, the ability to use all of that imagery to build the environment model around the car will become possible. The second thing, of course, is that the car has to become self-aware. Self-aware as in situationally aware. It has to be able to see and understand what is happening around it. In front of it, beside it, behind it, become situationally aware. In order to lead to an autonomous driving car, we have to be able to do path planning. Based on the situation, based on the environment, the car has to plan its path. And of course, because none of this technology is possible on day one. And just as we are continuously learning, the car has to become software updatable. It has to become able to learn. It has to be heavily based on software updates over time. In a way, the car of the future is going to become a software-defined car. Software is going to become a greater aspect of it. So we imagine all of these cameras around the car being connected to essentially a supercomputer, a supercomputing processor, if you will. And that supercomputing processor, that computing platform we're introducing today, it's called the Drive PX. The Drive PX The Drive PX consists of two Tegra X1s. They could be working in parallel. They could be working as a redundant processor to each other. Combined, it has 2.3 teraflops of computing throughput, computing horsepower. It is able to connect to up to 12 high-definition cameras and process 1.3 billion pixels per second. 1.3 billion pixels per second. Now, to put that in perspective, these 12 cameras can be full HD, running at 60 hertz, and these dual TX1s will still process every one of those pixels. It is completely CUDA programmable with the latest CUDA 6.0. Thank you. And it introduces two technologies that are truly revolutionary. The first is a computer vision technology based on deep neural nets. And the second is a brand new technology called surround vision. But before I show you this, let me first illustrate the pipeline to you. And one of the reasons why it's so important to connect all of these cameras into a super processor. Now, these cameras that surround your car, it could be 3 cameras in the front, one with tight focal, long distance, one with wide field of view. It could be side cameras, it could be rear cameras, it could be internal cameras, it could be digital mirrors, smart mirrors. All of these cameras would feed into the Tegra X1-based Drive PX. Inside the Drive PX, all of those pixel data comes in to a crossbar, which is then fed to 2 powerful processors. 4 powerful processors. The VPE, the ISP first, which is responsible for the 1.3 gigapixels of data, has the ability to do white balancing, color correction, gamma correction, all kinds of image processing functionality. You could record all of this information into, of course, the data recorder inside the car. We could record dual 4K at 30 hertz. And then, of course, there's the 256 processor core GPU. Now, together, we're going to be able to now have access to all of the gigapixel information coming from all of these cameras. And together, now we have to figure out a way to create the environment, understand the situation that the car is in, find its path, and keep the drivers out of harm's way. Okay? So at the core, this is the block diagram. Now, once we get access to that information, in order to make sense of it, computer vision technology is necessary. To understand what we're seeing, computer vision technology is necessary. Well, one of the most important things we're announcing with the Drive PX is a revolutionary technology called deep neural net computer vision. Traditional computer vision basically works like this. Engineers code what is feature detectors, and they figure out if you want to detect a person, if you want to detect a car, if you want to detect a sign, engineers would go and engineer feature detectors that has the ability to represent and detect and classify those objects. They would then train it and test against it a bunch of known good and known bad images. This is what a pedestrian looks like. This is not a pedestrian. Each and every one of those objects, each and every one of those classes, if you will, has to be hard-coded by engineers. And they use a technology called SVM. These SVM support vector machines are able to detect a few objects. And state-of-the-art today can detect pedestrians, cars, signs, and lanes. However, if you want to figure out a way for your car to become situational aware, we're going to have to detect a lot more than those 4 things, and I'll explain why in just a second. We want to detect, of course, all of those things, but so much more. A revolutionary technology has emerged in the last several years called deep learning. Now, recently, we're starting to see a lot more understanding of the impact of deep learning. This is a technology that is only a few years old, revolutionized by 2 very important artificial intelligence researchers, one, Yann LeCun, and the other, Jeff Hinton. Yann is over at Facebook now, Jeff is at Google. Now what's happened is they recognize that neural nets are in fact a wonderful technology. However, it didn't have the benefit of several things. And recently there was an important paper that was written, and Wired picked it up. One of the 3 technologies was massively parallel and cost-effective processing. The GPU was named as one of the 3 important breakthroughs that made it possible for researchers all over the world to finally use deep learning in a productive way. The second is the vast amount of images, vast amount of voice data, the vast amount of data that we're able to access now. Because, of course, mobile computing, because of mobile devices, cameras, and voice recognition all over the place. And the third is new algorithms, that is what they're referring to, deep neural nets. Now here, this interesting graph that I show you on the right is the Olympics of computer vision and image recognition. This is ImageNet. Now ImageNet represents basically 1,000 classes. Your job is to recognize 1,000 different things. 1,000 different things. And then the contest basically consists of who can recognize with the greatest accuracy out of the 1.2 million images that is going to be served to you. 1.2 million test images, and you have to recognize 1,000 things. And whoever has the greatest accuracy wins. Now, they've been progressing for the last decade a couple of % per year, using the traditional feature detectors, support vector machines, engineers working really hard to detect more and more objects. All of a sudden, the GPU comes along, the deep neural network was invented, and bam, in literally just 1 year, it shot up from 74% to 84%, and now GPU-accelerated deep learning can now recognize images better than most humans. It's well over 90% now. Now here's what a deep neural network looks like. It's inspired by biology, and it basically works like this. It starts with the first principle that if you have a neural network and you have an enormous amount of input, a lot of input images, and an enormous amount of tagged output images, what it's supposed to be, if you have a lot of input, you have a lot of output, known good output, eventually you could train the neural net to recognize images by itself. Now this is a deep neural net. The training of it is intensely computationally intensive. And basically what it does is without any programming, except for setting up the neural net, the algorithm of calibration and retraining is extremely complicated. But after that, you let it go, and you run it for, as it turns out, before the GPU came along, months at a time. The GPU was revolutionary because we were able to take training sessions that would take weeks and months down to hours and days. Now what happens is this. You train this network, and you keep showing it images, and every time it's wrong, it makes a small change, and it tries it again. The search process eventually of figuring out how to weigh each one of those neurons. Each one of those circles is a neuron, and each one of those wires is essentially a synapse. There's a weighting on every single synapse so that depending on what you see, what patterns it recognizes, eventually it fires the neuron. Okay? So there's a neuron inside, in this particular example of detecting an Audi, there's a neuron in there for detecting a wheel. And that neuron is built up of small segments and curves, and maybe some hubcaps and stuff, and hubs, and eventually it builds up a wheel. Maybe there's a grill. Maybe there's some headlights. And it literally does this all by itself. It literally does this by itself. Now, of course, the training process is very complicated, and you need a processor with a lot of computation capability so that you can process this deep neural net and classify objects. Now, one of the things that's really cool about this, because each one of the layers of the deep neural network builds on the previous layer above it, before it. So on your right-hand side, or my left-hand side, that layer, the first layer, ultimately learns to recognize small segments, pieces of fragments of images. The layers next to it, the deeper layers, the hidden layers, might take these segments and turn them into curves. The layer after that might take a bunch of curves and turn one of the and recognize one of the neurons to be a wheel. Another neuron could be a grill. Another neuron could be the windshield. Another neuron could be the symbol of Audi. And so the beautiful thing about this neural network is once you've trained it, if you ask it, what's a car, it is likely very similar network as what is an Audi. And if we train it to recognize Mercedes, it would recognize Mercedes, and it would leverage the vast majority of the same network. Okay, so imagine running a program, it's highly nested, and so it becomes a very efficient program. Now, the benefit of this is notice the classification of recognizing a pedestrian and recognizing for example, a pedestrian is straightforward. However, if the vast majority of that pedestrian was occluded, a traditional feature detector wouldn't recognize that as a pedestrian because a pedestrian has heads and arms and legs. In this particular case, because this deep neural network has the ability to recognize subclasses, it would recognize that, guess what? It's got a head, it's got a couple of arms, even though it's missing legs. It's likely a human. It's likely a pedestrian. It's likely a person. Recognizing a car is something we can teach a traditional computer vision algorithm. However, different classes of cars, and maybe different classes of cars in different conditions. For example, if a school bus were to pull up relative versus a car, a school bus, the way that you would approach that condition, that situation would be very, very different. And if all of a sudden the lights of the school bus was flashing, again, you would become even more alert, even more aware of the situation. So just detecting the fact that it's a car is not good enough. If you detected a car behind you, that might say absolutely nothing. However, if you detected an ambulance behind you, you might decide to pull aside. So the important thing to recognize here is that recognizing and detecting objects is just a starting point of an intelligent car. That recognizing what the images are and the context of those objects is highly important. So let's show it to you now. Okay, we're going to show you deep learning. We've trained, before you start, we've trained over the course of the last couple of weeks, just a couple of weeks, we've trained Tegra X1 to recognize some things that you see on the roads. This is all trained with deep learning, and it's running on a deep neural network that's running on TX1. Okay, guys? This is Mike Houston.
So the first thing we're going to show you is deep neural networks doing some of the traditional computer vision techniques that you've seen. So in this case, we're actually going to detect crosswalk signs. So you see that we pulled this crosswalk sign. So again, the interesting thing here, as opposed to trying to train something like a hog detector, histogram oriented gradients, to recognize the diamond, we've just given lots and lots of examples of crosswalks as a tag for the neural network to learn. What's interesting about this technique compared to traditional computer vision techniques is the distance and accuracy at which we can detect things. So there's another crosswalk sign coming up that's very far away, right at the edge of what you would naturally be able to see to begin reacting to. So in a case like this, especially if it's busy and you're at high speed, this can feed back into the ADAS system to change your situational awareness, i.e. slow down even below the speed limits if you know that it's a busy pedestrian area. This is actually around the San Jose courthouse. So here's another one where we're grabbing speed limit signs, similar thing. As opposed to sitting there trying to train a specific sign detector, we feed thousands and thousands of examples of signs, and it learns the classes of signs. So in this case, a 30-mile-per-hour speed limit sign. Combined with this, we can also do pedestrian detection, including some hard cases. So you see there on the left, we've picked up these pedestrians. So those are sort of the easy ones you'd expect traditional computer vision techniques to get. There's more difficult ones, as Jensen mentioned, which is occluded pedestrians. So if you notice, behind that police car, there's a partially occluded pedestrian. And it turns out it's actually a bicyclist. So we see occlusion, we can't see the bicycle, and so we tag that as a pedestrian. And then as soon as we can see the bicycle, it gets redetected and reclassified as a cyclist. So one of the things we can do is detect street lamps.
Now, Mike, before you go on,
Sure.
For most people who are watching this, of course, this is computer vision. The video was obviously recorded a priori. Okay, the video is not live, obviously, but the processing is done live here. The video is going into the Tegra chip, and the Tegra chip has a deep neural network that has been downloaded to it, and it's been trained to recognize a handful of things in this particular case. Okay, so whenever there's a video, whenever there's an image that comes in to TX1 and has one of those objects that it has been trained to recognize, in this particular case and just some of the cases, and we'll show you a few more really cool ones, even an included pedestrian, it would recognize it. So the video is not live, but the processing is done live. Go ahead, Mike.
So in this case, you see that it understands that the left turn lane is actually a red signal and that forward traffic can proceed because the signals are green.
And so in this particular case, stop there for just a second. In this particular case, really what's really super cool is this. It's a bunch of lights. It's a bunch of red and green lights. However, once it recognizes, detects, and understands and classifies a particular light, it can also subclassify them into a red light, a yellow light, a green light.
Well, and what's actually more subtle about this one is real cameras in automotive today are actually monochrome, so we don't get the benefit of understanding if it's red or yellow or green. We actually need to understand the full position of the light. What you're seeing is actually a color video, but the processing is actually in a monochrome. So we actually have to fundamentally understand, first we have to detect the light, and then we have to understand the class based on the position of lights. Just like in some locales, lights are actually horizontal, not vertical. So again, those become another class that we've actually learned, and so we can process those classes.
Now you've got a couple of lights that you haven't figured out. It's called unknowns.
Yes, these are interesting ones. So the
them.
reason that they're unknowns is if you actually look at what's happening, we have these very strong oblique views. So the one on the far right, we're just about to pull past. It technically doesn't apply to you. But what happens in this case is we didn't train on oblique lights, because they don't matter generally for ADAS systems. So they actually fall out of the classifier. So we know it's a type of light, but we haven't been able to classify it down to the next level in this specific case. But the ones that are head-on, are the ones we concentrate on, and those are the ones we concentrated the training system on.
And so some of those unknowns, I'm going to come back and talk about in just a moment. Keep going.
Sure. So a particularly difficult challenge for most traditional computer vision systems is hard lighting conditions. Usually in research you see these pristine sunny day conditions. So this is a shot in the UK. So let me explain what you're seeing for folks in the US that haven't seen these types of road signs. So what we're about to come up onto are what are called matrix signs. So they're on a gantry and they're dynamic. So based on driving conditions, there'll be different speed limits. Okay? This is shot in the UK at nighttime in foul weather. And the power of the neural network allows us to handle the ambiguous nature of these lights and still detect quite well. So the first thing that we capture is that on this gantry, there's in fact a speed camera. So we're able to recognize, detect that, and classify it to let you know there's a speed camera here.
Well, that's probably the most valuable detection you can imagine.
So we've been able to read that this is a 50 limit speed sign. What's particularly difficult actually about these signs is they have an update refresh interval of 60 hertz, and we're driving a 30 hertz camera, so they actually blank out. There's certain frames that actually doesn't have a complete representation of the sign. The other note here is this warning on the left. It says Q. So what this means is there's congestion ahead that you're going to need to slow down. That's awfully important information if you're traveling at high speed. So as we continue down the road...
Now, if you could just pause for just a second.
Sure.
Just right now, you saw 4 objects classified in one scene. There were already 4 classes right there. It's one gantry, but there was a speed, there was a camera alert. There was also the fact that there's going to be a congestion up front. Okay, there were already multiple things that were being classified. Keep going.
So as we continue going, we begin to get congestion. A couple of things begin to happen. So we actually begin to pick up and recognize that there's actually braking traffic ahead. So if you notice, there's one car that's beginning to brake because the traffic is slowed in front of him. As we continue to close, we begin to get more triggers. So as opposed to relying on a radar system or something else or a collision avoidance system, you can actually detect that there's upcoming traffic and braking that's required. So you can get to smoother stops without harsh stops. All right,
That's not too bad.
so why don't we go to Vegas? So one of the other things we can do is, in this specific case, we're doing vehicle detection. And so we can actually subclass vehicles down. So you can make different driving decisions based on the class of vehicle that you have. So in this case, we're classifying the vehicle. So you can see there's 2 SUVs in front of us. The bar on the bottom represents the confidence level. This is how strongly the neural network believes that what it's saying is this class. So it's driving by the wind. So you see that we have a passenger car tag there on the left. An interesting thing happens as we close in on this intersection. So we begin to get a strong number of detections. And we still have the 2 SUVs that we've been tracking in front of us, but we've now picked up a heavy truck on our right. It's actually one of these advertisement trucks you guys see drive around here. An SUV. On the other side, we have a truck and a van. So a few frames ago, it probably went by too quick, but you guys can see it on the hands-on. It actually classified that hotel transport van as a heavy truck because it had just this base initial view. But as we close in on the object and we get more views, the neural network gains more information. It's easier to better classify the object.
Okay, so the important things, some of the important things that Mike is talking about here, if we were to engineer each feature detector for each object to recognize, we would have to engineer a feature detector for a van, a feature detector for an SUV, a feature detector for a light truck, a feature detector for a sports car. Now, of course, we're simply having fun here. We're simply having fun. We're going to show you examples of how this could be very useful. But obviously, if you were to detect a fire engine, an ambulance, you would really behave very, very differently. Now, using traditional techniques, you would have to go and engineer each and every one of the feature detectors. In this particular case, frankly, we just let the computer went and train and learn these different subclasses. They're all cars, but within the subclasses, we also taught it that this particular car is a truck, this particular car is a sports car, this particular car is an SUV. We can teach it this particular car is an Audi, this particular car is a Mercedes, this particular car is a Toyota. Okay? So these type of subclassifications from one major classification is one of the things that you can do with basically a deep neural network, which each one of the layers is built on top of the other ones. They're all essentially cars. They have wheels, they have windshields, they have grills. A really, really powerful new technique for teaching your computer how to recognize images. Now keep going.
So to actually give you a few more statistics on this about the data involved, so this is done from 40 hours of captured video, and the neural network training time is 16 hours on a Tesla K40 GPU. It's a very fast turnaround time.
It's pretty amazing what the neural network figured out how to do in just a couple of weeks' time. Okay?
So there's a couple of actually interesting things in this clip. So one of the problems with traditional computer vision is that car on the left zipped by us. And so if you purely base your technique on frame by frame or pure optical flow, it actually breaks because the features move so fast and the angle of the car in response to the camera changes so fast. What happens over a couple of frames with the neural network is because we gather those views, we're able to discern very rapidly that it's a passenger car as opposed to anything else. A similar thing when you detect things like pickup trucks that are work trucks, especially off to the side, you may make a decision that they pull out. And so you may make different decisions based on that. But we don't purely have to deal with just front-facing cameras. Sometimes rear-facing cameras are awfully important. So in this specific case, when we get ourselves into trouble and police are following you, you need to know that he's about to turn on your lights and, oh my God, you're about to get pulled over. So you better recognize that as a separate thing. I mean, a autonomous car can still break the law. And you need to be able to pull over. So even if it's not your fault, if it's an emergency vehicle in the US, it's a big deal. You need to actually move to the right.
Yeah, that sounds great, but what I saw you do just now, it appears that we were accelerating. We're trying to pull away.
So we're coming
All right.
we're coming to a stop.
Okay, thank you very much. Everybody, Mike Houston, machine learning. All right, this is deep neural nets, deep learning. The neural nets learn itself. It takes the things that we ask it to learn how to classify and breaks it down into layers and layers and layers of the neural net. It's extremely computational intensive, but if you have the computational capability, just imagine what you could do. And so these are just a couple of weeks of training. We've recognized a whole bunch of different types of cars. We could obviously recognize a whole bunch of different types of pedestrians. We can recognize all kinds of different animals. We can recognize all kinds of stuff. Now, once you become able to recognize your environment around you, and you have an environmental map, you become increasingly situation aware. And after that, of course, it's algorithms that would be applied running on a supercomputer, in this case a TX1, to help figure out what is the best course of action depending on what the car sees around it. Now, the way that we do it, this deep learning architecture starts with a supercomputer. And what you're looking at here is the Nvidia GPU supercomputer, a bunch of CUDA GPUs that are used by the same people who are using, whether it's Facebook or Google or Baidu or Yandex or Microsoft or IBM, who are using our CUDA GPU for deep learning. And here you would take a whole bunch of image, training data, training sets, with data scientists, guide the computer to learn to classify certain objects. Okay? The more data that you have, obviously, the more types of classes of information, the more types of things you can train the computer to recognize. What comes out of the supercomputer is a trained deep neural net. These are deep neural net parameters. Neurons with weights on the synapses. Those weights are called parameters. In the case that you just saw, those deep neural net parameters are loaded into the TX1. Now, everything that you saw just now consumed less than 10% of TX1. And we were recognizing a handful of classes. So a TX1 was processing 2 megapixels of information at 30 frames per second, classifying a handful of objects. I forget exactly how many, but call it 5, 6, 7, 8. And it was doing that with less than 10% of the overall horsepower of one TX1. So let's say that one TX1 can process and classify 75 objects at 30 frames per second, then 2 can classify 150 or so. 150 objects, all kinds of pedestrians, situation, all kinds of cars, all kinds of animals, all kinds of conditions. It can classify for forward-facing camera, rear-facing camera, even side-facing cameras. So now we're classifying and understanding the environment around the car. Now you also saw there were some that we weren't sure what we were looking at. Whenever the threshold is too low and we're not exactly sure what we're looking at, the probability of understanding it is low, and so we would tag it as unknown. That particular unknown image would then come back, would be sent back to the data center. The data scientists would reclassify and figure out how to learn how to recognize that object. And of course, one car not recognizing something updates the image to the cloud, retraining happens, and every single car is updated simultaneously. So you imagine, over time, this connected car architecture with a super mobile chip, with deep learning, has the ability to continuously learn the environment around it. It would start off being pretty darn smart, but over time it would continue to learn, just like all of us. This TX1, we put it to the ultimate test. This is the LXNet. This is basically ImageNet. There are 65,000 neurons in the LXNet, this network. 65,000 neurons, 60 million parameters, all loaded into TX1. And it's being asked to classify 1,000 classes. This is basically the ImageNet test. Running the LXNet, which is one of the highest performance ImageNet deep neural networks, we're able to classify 30 images per second. 1,000 classes recognizing from 1.2 million images. And so as you can see, we can recognize all kinds of interesting things. We recognize very accurately a German Shepherd. You could see a child. There's a hat, a child, and a bicycle in that particular image. Recognizes, of course, a van, bicycles, taxis, and speedlights. Okay? So one of the most important things in TX1, the Drive PX, is the deep learning, deep neural net computer vision technology. Now today we're really quite honored to have one of our closest partners here. Audi has been, I've been working with the Audi team for almost 10 years, and it's been a great pleasure working with them. There are several things that's really amazing about the Audi team. 10 years ago, they came and explained to us that one day the car was going to be rich with computing technology, and that it's going to be a supercomputing platform on wheels. And that one of the things that they have to do with great imperative and great urgency is to align with the rate of innovation of consumer electronics, and yet recognize that the car computer is so software rich that software compatibility and software reuse from generation to generation was important. They invented the modular computing architecture for the car. They also were the first to recognize that in the future, your car will need a visual supercomputer, so that it has the ability to see and understand the environment around it. Last year, with Audi, we announced the ZFAS autonomous driving computing platform. To join us here on stage today, it's a great honor for me to announce that Ricky Hudi has joined us, and he's going to talk to us about some of the developments. Ricky, great to see you. Happy New Year, first of all.
Hi, Jensen. Thank you.
This is Ricky Hudi. He's the head of electronics of Audi. He's the visionary behind all things computing inside the car. And if you look at some of the great achievements over the years of the work that you've done, it's just utterly fantastic. And Ricky, maybe you could tell the audience some of the areas of development that you're really excited about, that you're really proud of, and you want to share with us.
Yeah, first of all, Jensen, thank you. Hi to all of you. It's really a great pleasure to be on stage on the press conference today with you. And a lot of the things you've mentioned already about the visual computing up to the driver assistance systems has a lot of common DNA of our two companies, which we created in the last 10 years. Let me cover a little bit this slide you see here, because it contains 3 generations. First, what Audi and Nvidia have already successfully on the market. We will explain it to you together in a short time. Second, what we are doing right now. And third, what are our visions in the very near future. As you mentioned, Jensen, one of the biggest challenge for us together was to bring the development cycle of the automotive computing platforms together with the consumer world, and especially in the infotainment systems and in the instrumentation clusters. And when we sat together many years ago, we had the idea to separate the slow-moving parts in the car from the fast-moving parts. And the MMX module, which has a size of a double credit card, is the crucial part of our modular infotainment platform. And what is already on the market is, beginning of 2013, the MIB1 with Tegra 20. In 2014, just 1 year later, the Tegra 30 with a real cool, absolutely high-performance instrumentation cluster in the new Audi TT. We call it virtual cockpit.
The digital cluster and the infotainment system merged into one.
Absolutely.
Into a virtual cockpit.
And another year later, right now, this year, we bring the Audi smart tablet on the market, which we announced last year. And another year later, we are going to bring products with a K1. So it is not something which we are talking about in the future. We have this together on the market.
Now, because of the design methodology and the architecture approach that you guys have taken, what used to take 5 years from the introduction of a new technology to the time that it hits the road has been shrunk down to essentially 1 year.
Yeah.
Every single year that we're here, there's a new product that you've announced based on the technology. I mean, you are at the pace of consumer electronics today, based on the architecture that you've invented.
Last year you announced CK1, and the next day in our press conference, you were part of that, we announced that we bring products with a K1 on the market. This level of speed and flexibility, which brings us this architecture, and although this partnership of our two companies is really a paradigm shift in the complete development of such system for the automotive industry.
Now, one of the things that I just want to emphasize the importance of the architectural strategy you've taken. You observed that a car company cannot treat every single car like a separate computer.
Absolutely.
You cannot build every single car from scratch from the beginning. That the amount of software reuse from every single car in Audi has to be as large as possible. And as a result, you can move very fast. The quality of the software gets better and better every day, and the investment that you make is preserved.
That's right.
A great vision.
Let us talk about the picture in the middle. This is the Audi Prologue, a concept car which we showed in the LA Motor Show 2 months ago. And it gives you the outlook of the future interior of the Audi cars. And I promise you, Jensen, this is not only a concept car.
No, I've seen it working.
This is the shape of the future
Wow.
our cars are going to look like in the future. And what you see here is a virtual cockpit like we introduced already in the TT and all now following cars. It's a touch display in the center. It's a touch display for the passenger. It's an OLED display which folds up when you start the car. It welcomes you. And what I need from Nvidia is computing power, because display, performance, high resolution, that means pixel, 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 pixel.
Yeah.
And that was the reason why we've decided the K1 for this future cockpit computer.
That's beautiful. That's beautiful. You know, anybody who needs more pixels is just music to my ear.
Yeah,
that's just incredible.
And therefore, in the Drive CX development platform, as I mentioned, there is a lot of common DNA where all these things we have done successfully in the last years, and which we are developing right now for the near future, has been implemented.
And that just shows the front seat.
Yeah.
Don't forget the back seat, right? Just more pixels. Just brings me joy. Brings tears to my eyes, actually.
In the back seat, we have the mobile Audi smart tablets, powered by Nvdia. So now let's talk about the third thing, the piloted driving, or as we call it at Audi, or autonomous driving. What you see here is Bobby. Bobby was, in October 2014, the first autonomous driven car driving a high-speed lap on the famous Formula 1 Hockenheim ring in Germany with 240 kilometers per hour, nearly the same time for a round lap as the best drivers, and we finished it successfully.
Now, I don't know if you guys have noticed, there are actually nobody in the car.
There was
you just have to take a closer look. There's actually no human in the car.
Go to YouTube and watch Audi RS7 Hockenheim. There is a very famous speaker also who makes a comment. But now and today,
most people have never gone 240 kilometers per hour.
200.
Yeah, 200. Pretty amazing.
But today there is another absolutely milestone in the history of our development of piloted driving. Today we started the first long-distance piloted driving tour from the Silicon Valley, 2 days to Las Vegas, and with 5 trained US journalists. They have a certification of the Department of Motor Vehicle of California. They finished already the first day successfully. They are now in Bakersfield. And nothing wrong happened. Everything worked perfect and fine. And they are going to arrive tomorrow. And the name of this car is Jack. So if you Google a little bit in the internet, you can see it. But now let's talk about the development platform and what is necessary for that. The in-car image recognition we have established the last years successfully in our cars allows already very powerful functionality, like the high-speed lap or the test drive, what we're doing to now. But to enhance it in future, as you pointed out, we chose the CFAS architecture, and we chose to use the Nvdia CUDA technology. Exactly for that, what you have mentioned, that we can do the massive parallel processing already on board, the deep learning, the machine learning. The car gets intelligent more and more with every situation. Via a high-speed LTE connection, we refer this to our cloud architecture, also with CUDA processing, and exactly this is the way to combine the onboard recognition with a powerful enhancement of machine learning. And yeah, that's the future
That's amazing.
of self-driving cars. And believe me, it will not last too long when the first self-driving or piloted cars will come to the market from Audi.
That's really amazing. Thank you. Ricky, thank you very much. Thank you. And congratulations on your achievement today. I couldn't believe that you talked five journalists to sign a disclaimer. But I do it in a heartbeat. I do it in a heartbeat. That's really exciting. I want to show you one last thing that combines all of the things that I've been talking about. You got the Drive PX with the ability to connect all these different high-speed cameras. It brings it into the Drive PX computing platform powered by TX1. TX1 then figures out the environment around it. And then from there, we can apply deep learning, computer vision, and other computer vision techniques to better become situational aware. The technology we call is surround vision. Surround view is taking multiple cameras and stitching them together. Surround vision is being able to look at and understand, see and understand the environment around the car. To show you what surround vision can do, Jem is going to give us a demonstration of this incredible technology. Jem?
Thanks, Jensen. Okay, so the first thing we're going to show you is the simulator that we've developed, which is what you see on the screen right now, which is a photorealistic simulation environment for testing computer vision algorithms. So one of the challenges with computer vision is that it requires real cameras and rigging up of situations and cameras on vehicles and other things if you want to test real autonomous driving types of algorithms. And a lot of times that configuration is challenging. So what we thought is, why not do it in a virtual world, especially since we have such expertise in realistic rendering and photorealistic rendering and physically based rendering. We developed this simulator to do exactly that. So this is a parking garage that's based on the parking garage at Nvidia headquarters in Santa Clara, California. And Curtis here is going to drive the car around this environment to give you a feeling for what the space looks like.
Now remember, this is completely real-time 3D. This particular parking garage is real. It is really our parking garage. I think some of the cars, for example, the Ferrari 430, there's quite a few Ferraris. Maybe lots of Audis. And so this entire environment is designed in 3D, and everything is rendered in real time. As you know, we simulate as a company. Simulation is deeply rooted inside the culture of our company. We simulate obsessively so that our chips are perfect. We simulate obsessively so that our algorithms are perfect. So it stands to reason that we would create a simulation platform for autonomous driving.
So we can reconfigure this environment as well. This is not a static environment, so in addition to driving through it, Curtis can change the configuration of which spots are filled and what cars are in the spots. And indeed, we can actually even just fly around in the environment, fully real time, and click on the spots and reconfigure them to different vehicles, or even make the spot completely empty, or whatever you'd like.
Okay.
So this is the first part, which is the actual simulator. So another component of the simulator is it's not enough just to render this viewpoint, but we also need to generate inputs that would run into computer vision algorithms, and that means we got to attach cameras to this car. So let's transition to the other visualization. So what this is showing here, the center image is running on the same machine that you were just seeing. The four images around it represent the views from different cameras that are attached in this virtual environment. And those cameras are actually being rendered on separate machines. They're doing real physically based fisheye renderings. Fisheye cameras are very common in automotive platforms. And then and they're fully synchronized with each other. So they follow the car. There's a camera in front, one on each side, and one in the rear.
Now imagine the power of this platform as a result. I mean, he really has, there are 5 high-end Nvidia GPUs simulating this virtual environment. The beautiful thing about this is now we can change the virtual environment with great ease. We can change the environment around it, we can change the lighting around it, we can change, obviously, the geometry and all the obstacles around it. And this particular simulator behaves physically accurate. The rate of the wheel turning and how quickly the car is moving is physically simulated. When a car, well, we could collide against another car. Every single car has collision detection. And so everything, okay, notice the triangle, the two objects don't go into each other. There's collision detection involved. And these 5 GPUs are rendering the 5 views that you're currently seeing, and these views are then translated into video input that the Drive PX will now use for recognizing the environment around it.
That's right. So the next part of the demo, what we're going to show is, given this data that the simulated environment generates, which is the fisheye input camera inputs, we're going to show some computer vision algorithms on which we'll base the Drive PX features. So what this visualization shows on the left, we've got the 4 camera inputs. Those are generated in the simulated environment. It will look familiar to you. It's the parking garage we just showed. On the right is one of the surround vision visualization modes we have, which takes the 4 camera inputs and warps them to show a simulated top-down view. I'll let this run a little bit, and you can see as we move around through this environment, the camera's updating as you'd expect. So one of the first visualizations I'm going to show is what's called feature tracking. So this is a computer vision algorithm. They basically identify salient points in the images. So this is all just in 2D. And what it does is basically tracks them from frame to frame. So this is an important building block in doing computer vision, because it allows you to actually know that a point from one frame to the next, how it moves from frame to frame. So what we can do if we have that visual, once we've done the actual frame, the actual feature tracking in the 2D, is we can switch to...
Jim, don't switch yet.
Okay.
So what you saw earlier, the previous set of scenes were being generated on the simulator. All of the images you're looking at now are what is seen by Tegra X1. These are being processed on the Drive PX. Does that make sense? Previously, the previous scene was a simulation of the parking garage. Now, that simulation turns into video input, and you're now looking at all of the data that's being processed on the Drive PX.
That's right. So we can advance it a little bit more and then switch into what we call point cloud mode. So what this shows is, given the features that are tracked in the 2D images, what this does is in real time, using CUDA, based on both those features and their positions in the images and the poses of the cameras, which we determine algorithmically, reconstruct the 3D positions of the actual geometry in the scene. So if I pause it for a second, like right here, for example, I can actually rotate around this in real time, and it gives you a sense for the points in the scene and the structure of the environment around the car. So we can play it here a little bit more. So this is an important building block, because what we need is for the algorithms that happen after this, the real sort of intelligence and reasoning about the surroundings types of algorithms, we need them to know the structure of the environment so they can navigate, they can make decisions about where to go. And so the first step to that is generating the actual, a sense for the actual 3D geometry in the scene around the vehicle.
And so what you're looking at here, number one, we're modeling the environment. We're also understanding what we see. And now, as you saw, we're doing pathfinding. Okay, go ahead.
Okay, yeah, and if you're curious here, the colors, by the way, are basically indicate which camera those points came from originally. But they're all in the same 3D space. Okay, so that's what's called structure for motion. It's a very important fundamental algorithm in computer vision. And then the last step, the last thing we're going to show everyone is basically putting all of these pieces together. So what we see here, the image on the left is the simulator image that we showed initially. It's the same environment. What we showed earlier when we were showing the simulator was actually being driven by a human. We were driving around just using a keyboard. Now what we're doing is we're taking the images that we're generating by those 5 servers that Jensen talked about, sending them actually over a network to a client which is doing the computer vision processing, analyzing the images, doing structure from motion, and then driving commands back to the server to find a path through this environment which finds a parking spot, a valid parking spot, and parks in it without colliding with any obstacles.
The processing for reconstructing the 3D environment, creating the point cloud, and the pathfinding is run on the car. Okay? The only thing that's being done in the server is the simulation and generating what is essentially virtual video input that comes into Drive PX.
Exactly. So let's go ahead and try to find a parking spot. So what you see on the right and the right side of the right are, again, those images, and that's the only information that the pathfinding algorithms and the computer vision algorithms have about the world around them. Right? So the server generates those, the simulator generates those. Some reasoning is done on those images. 3D points are generated so we understand the structure of the environment around the car, and then we can determine where to go and where not to go based on that 3D structure.
Now they tell me, I asked them why it's going so slow. They tell me that's 5 miles per hour. and it seems slower than 5 miles per hour, and they accuse me of never having experienced 5 miles per hour, which probably is true.
Yeah, this is how you're supposed to drive in a
I'm
parking
not sure
garage,
that I've
Jensen.
ever experienced, yeah, well, apparently that's the speed limit in our garage.
So another visualization we have here, if you could enable the obstacle map, is something we call an obstacle map. This is showing basically, given the 3D points that we showed earlier from the point cloud, we can actually do some further reasoning about that, where we determine which of those points correspond with obstacles, things which are undrivable, and which ones are not. Which ones are things like the floor, the ceiling of the parking garage, things which are not obstacles and so can be driven on. And so what we see here is, as the car navigates a space, the green line is the path that the car is following. The red points, areas of more red density are areas with more obstacles in them, and so they're places that we cannot go. And additionally, one visualization you're about to see now, because we found a parking spot here. You see there's an empty parking spot on the right. It's determined that it's a parking spot because there's 2 sets of criteria that we need for determining if something is parkable. One is that it has no obstacles in it, and the second is that it is actually a parking spot, right? We don't want to park in the middle of the garage where there's no parking spot. And so a parking command and a parking algorithm is executed, and we successfully park in the parking spot.
Now, from the car's perspective, this is a parking lot it has never seen before. This is from a car's perspective, this is a parking lot it has never seen before. We could change the objects so the 3D space around it can always be new. And it figures out the environment, it becomes aware within it, and you saw earlier we could train the network to detect a person, a kid, so when they see a kid, when the car sees a kid, it would stop. Let the kid get away, and then continue its pathfinding. Now, of course, if we could do this part, the next part is super easy. Your phone, literally, we got out of the car just now, right? Right when we got to the entry of the parking lot, it meanders and finds its way through. It's never seen this environment before. It meanders, and it doesn't matter what it is. It'll meander and eventually find a legal parking space. When you're done with dinner, you say, come back to me, retrieve the car. It becomes the auto valet. That car now meanders back out, pathfinds, and eventually gets back to the driver. Okay? So what you saw is a great deal of technology that we just put together in the last several weeks. It starts with Drive PX, powered by Tegra X1. All these different cameras are coming into it. From those cameras, we understand the environment. We become situation aware using deep learning, deep neural net, computer vision techniques. We can classify all kinds of objects around it. And because there's a supercomputer essentially in TX1, we could use it for reconstructing the 3D space. We can use it for pathfinding, and as a result, start on the road, on the journey to autonomous driving cars. We announced 3 things today. 1, Tegra X1, the world's first 1 teraflops mobile superchip. Its performance is necessary to power our 2 other announcements. Drive CX the most advanced digital cockpit computer, allows us to drive multiple displays with computer graphics powered by the Maxwell GPU so that the graphics could be rich, beautiful, and also very high resolution. We showed you a material rendering technology that is embedded within our Drive Studio software stack. We also showed you Drive PX, the second computer inside your car, which will become the platform by which autonomous driving, autopiloted computers, autopilot cars will be built upon. Thank you very much for joining us. Please enjoy all of our hands-on demonstrations, and congratulations for the Nvidia team for pulling this off. Thank you very much.
Ladies and gentlemen, please head to the reception area for cocktails, food, and demos.